Good evening. Welcome to the new video of probability series. And this video we will talk about expectation of a random variable. So we know already what is random variable by the previous videos, and so definition 1.9 will show you what is the expectation of the random variable. So in the probability space omega fp, a random variable psi, which is a map that defined from omega to r. It's not just a map, but it also a semi-algebra measurable function according to the definition of a random variable. So psi is said to be integrable if psi satisfies this condition. It means that the base integral of the absolute value of psi over the domain omega is less than infinity. So this is, the first statement is about integrable function. So uh, if psi is a integrable function, if psi satisfies this condition, then the function e of psi is equal to the integral of psi, the base integral of psi over the domain omega is called expectation. And this function exists because psi is the integrable function. And for integrable function psi in the probability space omega fp, we say that psi is belong to the space L1 of omega fp. It means that the base measure or the base measure on the probability space. So after we know about the expectation of a random variable psi already, now we go to another uh, part about moment generating function, or we can call it for short MGF. So what is MGF? We start from the probability space, the same as in the previous definition. In the probability space omega fp, that a random variable psi is a mapping that maps from omega to R with CDF, or cumulative distribution function, that we denote it by f psi. And you know already what is the CDF, or cumulative distribution function of a random variable. So the moment generating function of a random variable psi denoted by m psi t, where t here it is the t here it is belong to R, and the formula of the moment generating function is equal to the expectation of e to the power psi multiplied with t. And in this case, we can also write it as the integral form also from the formulas of the expectation. Oh, from the formula of the expectation, we know that the expectation e of psi is equal to the integral, the Lebesgue integral on the probability space that defined like this. But in the case that psi is the absolute continuous random variable, that we know the probability density function of it. So this formula we can also write as integral from minus infinity to plus infinity of uh, psi or h, something like that, multiply with here with h multiplied with the PDF of h and the. So it is a problem of change measure from this to this. So I won't talk detail about it, but I will use these formulas to find the moment generating function. Okay, so this one we can use the formula of the expectation. Then we get e to the power xt f of x dx, where t here is belong to R, and provided this expectation exists for t in some open neighborhood of zero. We have to know that not all kind of random variable, not all kind of continuous, I mean continuous random variable or absolutely continuous random variable that have moment generating function. Some random variable doesn't have, I mean, they don't have the moment generating function. So in this case, if this, I mean, this expectation does not exist in, I mean, in the open neighborhood of zero. So in this case, we say that that random variable does not have MTF or moment generating function, or this integral is not converged, or this integral is not converged. We say that, oh, this random variable doesn't have a moment generating function also. So totally there are two cases. I mean, I talk about two cases, but maybe there are more than that. I mean, two cases that I talk about is if the, I mean, expectation, if the formula does not exist in the open neighborhood of zero, and one more thing, this integral is not converged. So we say that the random variable do not have MTF or moment generating function. Okay, so what is, I mean, what is the benefit of the moment generating function? So from the name of moment generating function, if we know it, if we know or if it is exists, it can help us to find the moment of that random variable. How can we find it? I mean, to find the moment of uh, a random variable psi, for example, we want to find psi to the power k, something like that. It is equal to the derivative of m psi t at the value of t equal to 0. Derivative of uh, the moment at the value of t equal to 0. And in that case, we can use it to find the moment, to find the moment of a random variable, where k here is belong to n. So, what is the moment can tell us about the information of the random variable. For the first moment, I mean, in the case that k equal to 1, e of psi, it is the expectation. And in the case that k equal to 2, so equal to 2, it is the variant, but in the case that the expectation is equal to 0. It means that the variant of the central case, and if k equal to 3, if k equal to 3, then it is like the standardized moment is the skewness. I mean, it's not just a moment, but it have to divide by the power of the standard. I mean, the standard deviation we divide it by sigma to the power 3, and this one will tell us about skewness. Skewness of a probability function. It is tell us about asymmetry of the graph between, around the expectation. And in the case that moment equal to 4, and we divide it, we scale it by sigma to the power 4, it means that the standard deviation of it, then it will provide us the information about kurtosis. Yes. And so these are the benefit of the moment. When we know the moment, we can know about expectation, about variance, about skewness, about kurtosis. But how to uh, how to find the moment? We can use the moment generating function to find it, but not all random variables that have moment generating function. One counter example is the log normal random variable. Log normal random variable, they have moment, but it doesn't have moment generating function. Yes. So this is a counter, a counter example about a random variable that does not have moment generating function. Okay, thank you for watching and see you next time.